We're going to work through one more solution stoichiometry problem. In this case, we have a chemist who adds 41.56 milliliters of 0.25 molar sodium hydroxide. Just let's remind ourselves that sodium hydroxide is NaOH. And remember, sodium has a plus charge, OH has a minus charge, so they can pair up 1 to 1, to 25 milliliters of phosphoric acid. So we haven't learned necessarily the names of acids, but there's a quick way of doing it. Phosphoric acid, if you try to match that name to a polyatomic ion, it sounds a lot like phosphate. And it is an acid made out of phosphate. Remember, phosphate has a -3 charge, and we also know that acids always start with hydrogen, which have a positive charge. And for those to make sure that all those electrons that phosphate wants to get are given by the hydrogen, we have to have 3 hydrogens, so it's H3PO4, and that's what you would call phosphoric acid. In some cases, acids aren't polyatomic, including polyatomic ions, in which case you would use the word hydro. So for example, this here does not have a polyatomic ion, it's just a single anion, and we call that hydrochloric acid, or this one hydrosulfuric acid. But if it does not have the term hydro in front, we know that it is polyatomic. We look at the name that closely matches the name of the acid and just write a hydrogen in front of it. So that's just a quick lesson of how to name acids. So we start off by writing the chemical formula, and equation. We know that we have NaCl and we have H3PO4, and we want that to be neutralized. So we know that water is always going to be formed, and in this case our salt, we call it, what's left over is going to be, my apologies, I wrote the wrong one here, didn't I? This should be, there we go, should be sodium hydroxide. So in this case, our salt will be Na and then PO4. Now remember, the PO4 has a -3 charge, and Na only has a +1, so we have to add a 3 over here. Now as soon as you see that, you can tell that the equation is not balanced, and so we do need to balance it. So we have 1 sodium here, 3 here. Let's place a 3 in front over here. We have 1 set of phosphates. So it looks like right now I have a total of 6 hydrogens. So if I place a 3 in front here, that gives me those 6 hydrogens. And then I have a total of 7 oxygens here, 7 oxygens over here. So it's now considered balanced. Let's add the information for each section. So I'm told that I have 0.04156 liters of sodium hydroxide. Notice that I instantly changed those milliliters into liters because we are always in molarity working with liters, not milliliters. And I have 0.25 molar solution, and that is my molarity. For my acid, it tells me I have 0.025 liters of hydrochloric acid. Again, I'm instantly converting the milliliters into liters, and I am looking for molarity. So we go back to our schematic that we have. Remember, this is our A value because it gives us all the information. This is our B because it contains the unknown. And it looks like I have volume and molarity, and I'm looking to get to molarity for B. So let's create a pathway. As the first two problems, I have volume, so that's where I'm going to start, and then move from there to molarity, to then moles, then from there mole B, and getting to molarity, which is right over here. All right, so let's write that schematic for ourselves. So we have volume A to molarity A to mole A, mole B, and then to molarity. And just a refresher for myself, remember molarity, I'm looking for units that are moles over liters, because that does equal molarity. Okay, and as you notice over here, I already have my liter value. So this value is going to be 0.025 liters. So really the only thing I'm looking for is moles. So let's see how this schematic will help me out with that. So I start with the volume that I have, 0.04156 liters of NaOH. Again, I'm going to write my moles written out. I have 0.25 moles of NaOH over 1 liter of NaOH. So that allows me to cancel these out. From there, I already have gotten to mole A. So I simply now need to use my equation to see what the relationship is. And it looks like my relationship is that for every 3 moles of NaOH, it requires 1 mole of H3PO4. Okay? And that gets me where I wanted to be, if you notice. Remember, I needed to have moles of B, and there they are, moles of B. So I can essentially stop right here, because remember from molarity I was looking for moles over liter. The liter I was given already, so that's 0.025 liters. Where did I get that from? I got it from right here of the H3PO4. So let me now just solve for my moles. And when I do my calculations, it works out to be that I have 0.0035 moles of H3PO4. And that gives me my molarity. Now, of course, we want to actually make that into a single digit, or not a fraction. And so when I divide those out, that works out to be 0.14 molar solution of H3PO4.